In this set of video, we're going to look at how we classify algorithms, and in this first video in this series, we're going to go over a few basics and underlying principles before we delve into some more of the complex stuff later on. So, as just mentioned, in this section of videos, we're going to look at how you can compare and classify one algorithm against another. The ultimate goal should always be to design algorithms which will, one, run as quickly as possible, and two, take up the least amount of memory possible. But first, we're going to cover a few basic concepts before we dive into some of the complexities in later videos. The four areas I want to cover in this video to get you up to speed is comparing algorithms by expressing their complexity as a function relative to the size of a problem, time-wise efficient algorithms versus space-wise efficient algorithms, permutations of a set of object or values, and a function maps one set of values onto another. Once you understand what these four underlying concepts mean, we'll be able to dive into the later videos and a lot of it will make a lot more sense. So let's get started. When comparing if one algorithm is more efficient than another, it's important to consider the complexity as a function relative to the size of the problem. So, what on earth do I mean by that? Well, let's have a look at these two algorithms here. Both of these algorithms are totaling up a set of numbers. So, for example, in both these algorithms, if we supply the integer 10, so n becomes equal to 10, both algorithms perform the calculation 1 plus 2 plus 3 plus 4 up to 10 and return 55. Now, you can check both of these and they do that exact calculation, but they do it in two very different ways. This one here we can see is using a for loop, and this one here is simply using a one-line formula. So, which of these two algorithms is better? Well, it all comes down to how well they perform as you scale up n. So let's take this for loop for example. There is one operation done here outside the loop, sum equals 0. So there's one instruction performed. Then we enter the for loop, and this line of code is going to execute each time the for loop goes round. So if n equals 10, this calculation will first be 0 plus 1 equals 1. Then it will go round, 1 plus 2 equals 3, 3 plus 3 equals 6, and so on and so forth. Now, we can see here that no matter how large this number n becomes, this section here, this line, is only going to execute once. The important part of this algorithm, in terms of its complexity as it scales, is this line. And as soon as n becomes anything other than a trivially small number, the amount of complexity that this single operation is adding on is kind of insignificant, so we can ignore it. We can see, therefore, that this algorithm performance declines in a constant and direct relationship as the size of the data grows. If n is 10, this will run 10 operations. If n is 1,000, it will run 1,000. Now let's take a look at the other algorithm. Here's the only line which performs a calculation, and it occurs once. It takes whatever n is, times it by n plus 1 and divides it by 2. The result is the same. But with this algorithm, it doesn't matter how large n is. We're only going to execute this single calculation. This algorithm always executes in the same amount of time, regardless of the size of the dataset. Now, this difference in their complexity as the size of the dataset increases is something we can actually measure. And later on in these videos, you're going to learn about big O notation. This is a special notation for classifying algorithms based on how their computation times grow as their input size grows. The second basic concept we wanted to cover was time-wise efficient algorithms versus space-wise efficient algorithms. Now, remember what we said earlier, algorithms can be measured on their efficiency, and this has two measures. time complexity, that's how much time they need to solve a given problem, and space complexity, the amount of resources, e.g. the amount of memory they require to solve a problem. Some algorithms are more efficient time-wise than others, whereas others are more efficient in a space-wise way than others. Remember what we said at the start of the video, the goal should always be to design algorithms which run as quickly as possible and take up the least amount of memory as possible. Now, the third concept we wanted to cover was the permutation of a set of objects. This is simply the understanding that the permutation of a set of objects is the number of ways you can arrange those objects. We call this the factorial. If you've done maths, you might be familiar with this. We would say 4 factorial, or we'd write it 4 exclamation mark, and this means 4 times 3 times 2 times 1. You can notice here that factorials get large very quickly. Indeed, if we took 10 objects and found all the various permutations and a way of arranging those 10 objects, it would be 3.6 million variations or permutations. The final area for us to cover before we move into some of the more complex videos is that a function maps one set of values onto another. So you're aware what a function is, and it's nothing more than the mapping of one set of inputs onto a set of outputs. One element of the input set always relates exactly to one element of the output set. Some key terms for you to understand here is domain, that's all the possible inputs of a function. Range, that's a set of all the outputs. And codomain, all the possible values that may be output from the function. If we call the function A and the codomain B, then we can say that function f maps domain A onto the codomain B, and we can write this in mathematical notation as follows.